hopefully from yesterday, you remember how to make a Taylor polynomial given some function. For example, the function y equals cosine 2x. Oh, good. All right. So what should we do first? At cosine of 2x, what does x equal? X is 0. And so what should the cosine of 0 be? It should be 1, right? And if we take the derivative of cosine of 2x, what do we get? Should get negative 2 sine 2x. That's our first derivative. And what does that give us? When we plug in 0, it should be 0. We should take the derivative of this, which should give us what? Negative 4 cosine 2x, which should then give us what value?
Negative 4.
Okay, that's our second derivative. Our third derivative should be 8 sine 2x, which will give us 0. And our fourth derivative is what we should need for our fourth order Taylor polynomial. Should be 16 cosine 2x, which should give us 16. Everybody good there? I hope.
Yes.
Okay, perfect. So what should this look like? It should look like 1 x to the 0 over 0 factorial plus 0, right? We can ignore that. That'd be 0x to the first over 1 factorial. Then we're going to have minus 4x squared over 2 factorial, and then 0x cubed over 3 factorial, and 16 x to the 4th over 4 factorial. Good or no? 1 minus 2x squared plus what? What does that come out to be? 4, 6, so 2 thirds x to the 4th. Does that look right? Everybody feel good about that? Or no? Okay, good. So if yeah, Nick, I don't know if we didn't simplify them all down every time. It's not a huge deal. Having it in either form is good. Generally they like to have it. Like if you're talking about just a polynomial, they want it to be simplified down. But it's nice to be able to look at it in this form for what we're about to do next with this, which is, let's see if we can write out what the actual Maclaurin series or the Taylor series at 0 is for the function cosine of 2x. So it'll be helpful to look at the one I've circled in red with all the factorials and all that stuff written out, because the simplified version doesn't always give us as much of an indication as to what the series itself should look like. So what's the first thing we should definitely add in here? What do we notice about the series that we're looking at, or from the polynomial? What do we notice is happening with each successive term? The simplest thing that's happening between them. Yeah, alternating signs, which is going to give us a -1 to the n. And then in the numerator, we've got x being raised to some power each time, right? It's being raised to the power of what? 2n. We've also got a constant out there. We'll deal with that constant in a second. In the denominator, it's always 2n factorial, right? But this is just the formula for cosine x. So we've also got the 2x in there. And so that's what's giving us these constants up here. And so what do those constants tell us? 2 to what power is being included into this every time? This one is 2 to the 0. This one is 2 to the second. This one is 2 to the fourth. Should be 2 to the 2n. So effectively what we could do is we could write this as the sum from n equals 0 to infinity of -1 to the n 2x to the 2n over 2n factorial. And we would note that this is the exact same series as it is for cosine x, except that instead of having an x to the 2n, we have a 2x to the 2n. What do you think the series would look like if we had cosine of 3x? Probably be 3x to the 2n, right? Or if we had 100x in there, it'd be 100x to the 2n. And so this is a nice pattern that we can use to manipulate our Taylor series, is that if I am changing the argument of a known Taylor series, like if I'm changing the argument of cosine x to cosine of x plus 1, I could just replace the x in the Taylor series for cosine with x plus 1, or replace the x with 2x, or replace the x with, negative x cubed minus 3x squared plus 5 or something, whatever we might have inside the cosine. Okay? And I'll write that out in a second on a slide a little bit later, and we'll do some manipulations with the one for e to the x and just see what the new one looks like. Does that make sense though? Should make life a little bit easier to write out ones that are relatively familiar. Okay. That's correct. Yes, Nick, it's just the x value that changes. So whatever the argument within that cosine is, it should change to whatever that is in the series. So we had cosine x in the original series, which gave us x to the 2n. If you put in a 2x, it's just the x that changes to 2x. Everything else stays the same. That's correct, Madhavi. Yeah, you could do the same thing with sine x. You can do the same thing with e to the x. You can do the same thing with any series, just like we did with the other power series, right? When we had series for 1 over 1 minus x. Well, if we had 1 over 1 minus 2x, we replace the x in that series with 2x. We do the same thing there, which is going to make life considerably easier moving forward for a lot of these series. And sometime tomorrow, I'll give you a list of all the series that you need to know, and just like know the series for them right off the bat, and then be able to manipulate them. There's, I don't know, 7 or 6, 7, 8 of them, something like that, that you should just know. So I'll give you that list tomorrow. Sound good so far? Okay. So next thing we need to be able to do is we need to be able to take a series and put it at x equals a rather than just x equals 0, which is what I accidentally posted yesterday before I posted the right thing. Writing a Taylor series at any value other than 0. It's just exactly the same, except that the x's get replaced with x minus a's. So if I were to take a look at, something that looked like 1 plus parenthesis, x minus 1 with some constant in front of it, plus some other constant, and it was x minus 1 squared, and some other constant, it was x minus 1 cubed, we would know that that should be a Taylor series that is generated at x equals 1, which would mean that the approximation used that you would use a Taylor polynomial for would be very, very, very accurate around 1 rather than being very, very accurate around 0, right? And larger the polynomial, the better the approximation would get for values close to 1. Okay? So it's the same exact formula that we've been using, except we're going to just replace the x's with x minus a's. Easy enough? Hopefully so. So let's see if we can find a Taylor series generated by e to the x at x equals 2. Should be pretty straightforward. Right? We know what f of x is, right? F of x is e to the x. F prime of x is also e to the x. F double prime of x, and so on. All of these are just e to the x, right? And so evaluated at x equals 2, these would all be e squared. So we're going to get a constant of e squared in front of all of them. So if we were to write out the series, not in a summation form, it would start off with e squared times our x minus 2 to the 0 over 0 factorial. Well, that's just e squared. And then we'd end up with e squared times what for the next one? Not x. Not x. Remember, we're centering this at 2, so it has to be x minus 2 over our 1 factorial. The next term would be e squared times x minus 2 squared over 2 factorial. And the next term would be e squared times x minus 2 cubed over 3 factorial. And the series would just look like the sum from n equals 0 to infinity of e squared times x minus 2 to the n over n factorial. Good or no? All right. So here's something we're going to do that's a little interesting real quick. Let's see if we can find a third order Taylor polynomial for this polynomial. What do we think the third order Taylor polynomial for this polynomial should probably be? That's right, Adrian. It should be itself. And so let's see if that's true. What is f of, we're doing 0, so what is f of 0? Should be -5, right? What about f prime of 0? What should that be? Should be 4. Yep. And what should f double prime of 0 be? Looks like it should be -6. And what should f triple prime of 0 be? Looks like it should be 12. Do y'all agree with those? Just by taking 3 derivatives there. I hope. Okay, so we should have -5 plus 4 times x to the first over 1 factorial. And then we should have -6, it's a -6, x to the second over 2 factorial. And we should have plus 12 x to the third over 3 factorial. And -5 is just -5. 4 over 1 is just 4. 6 over 2 factorial is just 3. And 12 over 3 factorial is 12 over 6, which is 2. And we end up with our exact same polynomial that we started with. Good or no? So if you were ever asked to find a third order Taylor polynomial for a third degree polynomial, it should just be the same function. If we're doing it at x equals 0. What if we were to do it at a different value? What if we were to look for it at x equals 1? What do you think it should be? Right, but what do you think the polynomial will end up being, Darius? Do you think it'll end up being what? I mean, we're going to replace it with x minus 1. And we're going to evaluate for different constants because it's going to be x equals 1. Let me write out my derivatives again, and let's try it. 6x squared minus 6x plus 4, 12x minus 6, and 12. So our original function, f of 1, what's f of 1? 2 minus 3, right? It's -1, plus 4 is 3, minus 5 is -2. And f prime of 1 ought to be 6 minus 6 is 0, plus 4. I'm writing the plus. It's 4, right? F double prime of 1 ought to be 12 minus 6, that's 6. And f triple prime of 1 ought to be 12. Note that we got different constants there, right? Different than we got with the original one. But when we go and plug these all in, we should get -2 plus 4 times x minus 1 over 1 factorial plus 6 times x minus 1 squared over 2 factorial, and then plus 12 times x minus 1 cubed over 3 factorial. And if we were to simplify all this out, let's see here, -2 plus 4x minus 4. This just becomes a 3 in front of that, right? So that's plus 3x squared, and then it's normally a minus 2x, so that'll be a minus 6x, and then a plus 3. And this is 12 over 3 factorial, which is 12 over 6, so that's 2 times the expansion of x minus 1 cubed, which is normally x cubed minus 3x squared, so that'll become a minus 6x squared. Then it should be a plus 3x, so we multiply that by 2 to give us a plus 6x, and normally it'd be a minus 1, so we'll multiply that by 2 to give us a minus 2. And if we put all of this together, -2 minus 4 is -6, -3 and another -2 makes -5. 4x minus 6x should give us -2x, plus the 6x gives us plus 4x. 3x squared and the minus 6x squared should give us a -3x squared. And we have a 2x cubed. And we'll note that centered at x equals 1, the Taylor polynomial, the third order Taylor polynomial of this third degree function is just that function. And what do you think would happen if we did it at x equals 2 or x equals 1,000 or x equals any value a? We would end up with this exact same polynomial. As long as this order is the same as the degree of your polynomial, no matter what value you center it at, when you expand it out, you will get the exact same polynomial, right? Because what are we doing? We're using a polynomial to approximate a polynomial. Well, you should just use that polynomial. Shouldn't need anything to approximate it. Pretty cool. Kind of amazing how all this stuff works out. Any questions so far? Everybody good? We're going to do one last quick thing. And I'm not going to like linger on this slide right here. But I'm just going to tell you what we can do. This is what I was saying we could do earlier. If we wanted to find the series for 1 plus cosine 2x, we could just substitute the 2x into the cosine one like we did. We could just add 1 to it, and then we just divide the whole result by 2. If we wanted to find the series for sine plus cosine, we just do a term-by-term summation of sine, the sine series plus the cosine series. And if I wanted to find the Maclaurin series for x times sine x, then I could just take the sine x series and multiply every term in it by x and just add that extra x in. Does that make sense to everybody? So we're going to do one of these. I know we're like 1 minute away from being done here, but it's really pretty easy. All you can do is just add this stuff in and get yourself a nice new looking series. So we're going to see if we can use the Maclaurin series for e to the x to write out a series for e to the 2x minus 1. So first off, what does e to the x look like? E to the x is 1, right, plus x squared over 2 factorial, and so on, all the way up to x to the n over n factorial, right? Everybody remember that, I hope? Hopefully so. That's one you're going to need to memorize. So what should e to the 2x be? I just need to replace all the x's with two x. Good? Or no? What if I subtract 1 from it? Well, I just lose that term of 1 at the beginning, right? What would that do to the series? Out here. Normally, exactly. So these had n equals 0 to infinity. The second one had n equals 0 to infinity. And this one, we could just bring up the index to n equals 1 to infinity. Right? Or if we wanted to, we could change these to say n minus 1s and keep the, well, we couldn't do that. We'd have to bring it up to be n equals 1s. Then we just divide everything by what? Divide everything by 3. So e to the 2x minus 1 over 3 would just be 2/3 x plus 2x squared over 3 times 2 factorial, and so on all the way up to 2x to the n over 3 times n factorial. And our final summation would look like the sum from n equals 1 to infinity of 2x to the n over 3 times that n factorial. Good or no?
Can you please go over why you raised the index again?
Yeah, so subtracting off the 1 from it took away that first term that we had. And so instead of now starting at the n equals 0 term, we're starting at that next term, which is the n equals 1 term.
Okay, thank you.
That makes sense, yeah. Guess I should have written all of these out, but I didn't. Any other questions on that?